Welcome to our quantum deep dive. Today we're exploring the incredible story of a physicist whose breakthrough discovery as a student, of all things, now powers the entire quantum revolution. It's a really fascinating question, isn't it? And the answer, maybe surprisingly, connects both of them to a single, brilliant idea that came out way back in 1962. And that student was Brian Josephson. His story is just amazing, and it comes to us from a really insightful essay by Jörg Schneeppert. So, okay, let's dive right into this.
So, here's the plan. We're going to follow Josephson's journey, from this young prodigy to a Nobel laureate. We'll unpack his revolutionary idea, and then we're going to explore the kind of dual legacy he left behind.
Right, so before we get into the man himself, let's just get a sense of his impact. We're talking about technology that promises to completely change our world. I mean, from quantum computers to medical sensors, so sensitive they can map your brain activity. All of it relies on his work. Yeah, and what's really wild about this list is that all of these modern marvels, they all trace back to a theoretical prediction made decades ago. We're talking qubits, the standard for the volt. I mean, it's just a staggering legacy, and it all kicked off with a single calculation by one student. So who exactly was this Brian Josephson? Well, he was born in Cardiff, Wales, back in 1940, and from a very young age, he just had this fascination with patterns and the laws of nature. And his journey was just meteoric. At Cambridge, he got completely immersed in one of the biggest puzzles in physics at the time, superconductivity. And he wasn't just learning about it, he was really picking it apart, looking for things that even the guys who came up with the theory hadn't seen yet. Okay, so to really get the genius of his 1962 paper, we need to wrap our heads around three key quantum concepts he was wrestling with. Think of them as the ingredients he was about to mix together in a completely new way. Okay, first up, superconductivity. The easiest way to think about it is like a perfect highway for electrons. When you get certain materials super cold, they lose all electrical resistance. Not just low resistance, literally zero. It's a pure quantum state you can see on a massive scale. Now, the electrons traveling on this perfect highway are called Cooper pairs, and they're really the heroes of this story. See, electrons normally push each other away, right? But in a superconductor, they team up and move in perfect unison, almost like a beautifully choreographed dance. The whole group acts like one single quantum object. And finally, we have quantum tunneling. This is the truly weird part. In our world, if you don't have enough energy to climb a hill, you just can't. But in the quantum world, particles can just, poof, appear on the other side. It's like a ghost walking through a solid wall. It completely defies our everyday logic. So, at just 22 years old, Josephson puts all these ideas together. He asked a simple question: what if these Cooper pairs, these unified quantum dancers, could tunnel right through an insulating wall? His calculations predicted something that seemed absolutely impossible. A continuous current would just flow right through, with no voltage pushing it at all. And this beautifully simple equation shows his first key insight. This is the DC Josephson effect. It was revolutionary. It showed that the current flowing across that gap was controlled by a purely quantum property, this thing called the phase difference. He basically found a way to make a hidden quantum dial visible as a real electric current. But his second prediction was even more profound. He said, what if you do apply a voltage? Well, the current doesn't just flow, it starts oscillating back and forth at a super high frequency. And here's the magic part. That frequency is perfectly, exactly related to the voltage you apply. This became the key to a whole new world of measurement. So a prediction this bold, it absolutely demands proof. I mean, you can't just go around saying current can flow through a wall with no power and expect everyone to just believe you. So the race was on, and believe it or not, the confirmation came astonishingly quickly. Just a year after his paper, a team at the legendary Bell Labs proved his theory was correct. They actually built the thing and measured the impossible current. The scientific community was just stunned. And within a decade, this work, which started as a student's little side calculation, earned him the highest honor in science. Let that sink in for a second. At only 33 years old, Brian Josephson was a Nobel laureate. His predictions as a student had literally opened up an entirely new chapter in physics. It was incredible. But the Nobel Prize wasn't the end of his story. In fact, for Josephson, it was a kind of turning point. His career took this really fascinating and, well, controversial turn, which created a dual legacy that people still debate to this day. Yeah, it's like there were two sides to him. On the one hand, you have this celebrated physicist whose work became absolutely essential. But on the other, he became what the Germans call a Querdenker, an unconventional thinker, a maverick. He started venturing into the highly controversial area where quantum mechanics and human consciousness meet, and that drew a lot of skepticism from his peers. But let's be clear, the practical legacy of his initial discovery is just undeniable. His effect isn't just a theory in a textbook, it is the engine inside technologies that are shaping the 21st century, from brain scanners to quantum computers to the official definition of the volt. You know, Josephson basically argued that science has to be willing to explore the unknown, even if it means risking criticism. He really felt that the mysteries of consciousness were a valued frontier for physics to explore, and he defended the need for science to stay open to those kinds of unorthodox ideas. But look, regardless of all the controversies, Josephson's initial breakthrough has become more relevant than ever before. What he figured out as a 22-year-old student is now right at the very heart of the next great technological revolution. And that's the bottom line, really. From Google's Sycamore processor to IBM's quantum devices, the qubits at their heart are, in essence, Josephson junctions. His insight from 1962 is literally the bedrock that the entire field of quantum computing is being built on today. It's that fundamental. His journey is such a powerful reminder that these huge, transformative ideas can come from anywhere, and it challenges us to stay open to the next great leap. We want to thank Jörg O.A. Schneppat for the essay that formed the basis of this explainer. For more, please do visit schneppat.de. Goodbye for now.
Schneppat.de is a private project by Jörg O.A. Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.